This lesson is on solving rational equations and inequalities, and I'll actually split this lesson into two parts for you. First part will be on solving rational equations, and second part on solving rational inequality. So I have an example here of a rational equation that I'll solve in the first part, and an example here of a rational inequality I'll solve in the second part. So first of all, what makes these rational equations or inequalities is that there are functions of x in the denominator of the expressions involved in those equations or inequalities. Also, notice the difference between equations and inequalities. Equations have equal signs, inequalities have inequality signs, either less than or greater than symbols. So when you're ready to get started learning how to solve these equations and inequalities, head on over to jensenmath.ca. Once you're here, go into the Advanced Functions course, and we are in Unit 6, the first lesson of Unit 6. You can get a blank copy of the lesson here, and you can fill it out as we go along. And then after the lesson is over, you can try the practice problems on the worksheet, and you can also click on Worksheet Solutions and check your work after. So let's get started. So before we start solving equations, I want to make sure you know how to simplify rational expressions and state their restriction. So first of all, what is a rational expression? A rational expression is the quotient of two polynomials. So the numerator and denominator are functions of x. And it's important to note that the function in the denominator cannot be 0. If the function in the denominator was 0, that would make the whole rational expression be undefined. So if there is an x value that makes the denominator 0 here, we would say that that x value is a restriction of the function. So let's simplify this. When simplifying a rational expression, you have to make sure you start by fully factoring it. So from the numerator, I can common factor out a 2. And from the denominator, I notice it's a quadratic in standard form. I can try and find numbers who have a product of 2 and a sum of 3. And the numbers that satisfy that product and sum are 2 and 1. This isn't fully factored yet. Did you notice the difference of squares right here? This follows the pattern a squared minus b squared. It's an x squared minus a 2 squared. So that factors to a minus b times a plus b. So in this case, the x squared minus 4 would factor to x minus 2 times x plus 2. And this is all over x plus 2 times x plus 1. Now that we have it into fully factored form, an important part of this process is being able to state the restrictions on this function. So are there any values of x that would make the denominator of this function become 0? Yeah. If this factor was 0, the denominator would be 0. Or if this factor was 0, the denominator would be 0. So x cannot be negative 2 or negative 1. If x was either of those values, the denominator would become 0, meaning the function would be undefined. And this is equivalent to the original function, it's just in factored form. It's easiest to see the restrictions once it's in factored form. And it's actually important that we stated these restrictions before we start simplifying this function. Let me explain why. Once it's in factored form, you can look for factors that cancel or reduce with each other. In the numerator, there's a factor of x plus 2. In the denominator, there's a factor of x plus 2. And anything divided by itself, that's 1. That's why I'm showing that I can cancel those out. But I shouldn't say anything divided by itself is 1. There's an exception to that rule. 0 over 0 is not 1. 0 over 0 is undefined. And this would be 0 over 0 if x was negative 2. But wait, we just stated here, okay, x can't be negative 2. So we're safe, we're allowed to cancel those out. This divided by this is for sure going to be 1, so we can cancel those out. So what I'm left with in the numerator is 2 times x minus 2 over x plus 1. And my restrictions are x cannot be negative 2 or negative 1. So what I have at the end here is equivalent for all values of x to this, as long as I ensure x cannot be negative 2 or negative 1. I just want to give you a glimpse into what this function would look like graphically. We're going to do quite a few lessons on how to graph rational functions, and this isn't the lesson for that. But I just want to give you a glimpse into it, and give you an idea about how these restrictions can show up on a graph. There are two possible ways a restriction could show up on a graph, either a whole or a vertical asymptote. Let's look at which one is which. So here's that function. It's a hyperbola. It's got two branches separated by a vertical and horizontal asymptote. Notice there are two x values where this function does not exist. At an x value of negative 1, there's a vertical asymptote. At an x value of negative 2, there's a hole. So the function doesn't exist at two x values. And those are the x values that we see written as restrictions here. I'll explain a lot more how we know that there'll be a hole at an x value of -2 and a vertical asymptote at -1 later. But for now, just so you know, this one I know is going to be a hole because that would make the original function be 0 over 0. And this one, the x value of -1, would be a vertical asymptote because it would make it be some other number over 0. And in this case, it would make it be -6 over 0. So I know that would be a vertical asymptote. But like I said, we'll talk more about that in a future lesson. For now, I just want to make sure you're able to simplify and state restrictions. So let's try another one. This one, I'll just focus on the factoring and simplifying and not over-explain those restrictions like I did last time. So there's a function of x in the numerator and denominator. We should try and factor both of those if possible. The numerator is a degree 3 polynomial function. We could test for zeros and do synthetic division, but it would be a lot quicker if we noticed factoring by grouping would work. I can common factor an x squared from the first two terms. And then I could common factor just a -1 from the last two terms. And when I do that, notice I have a common binomial. That's how I know factoring by grouping is going to work in this scenario. In the denominator, I'm going to start by common factoring out a 3 from both of the terms. Okay, let's finish factoring this. So let me common factor out that common binomial in the numerator. And then what I'm left with is x squared minus 1. In the denominator, do you see this here, this factor x cubed minus 1? That's actually a difference of cubes. The rule for difference of cubes, if you have something cubed minus something cubed, it would equal a minus b times a squared plus ab plus b squared. So let's factor it. It would factor to x minus 1 times x squared plus 1x plus 1. I should also notice here is a difference of squares, so I could factor that further as well. Let's just get it into fully factored form. So that x squared minus 1 would go to x minus 1 times x plus 1, all over that same denominator. Now that it's fully factored, we should state our restrictions. Are there any values of x that would make the denominator be 0? Well, 3 can't be 0, but x minus 1 could be 0 if x was 1, so 1 is a restriction. Can x squared plus x plus 1 be 0? Well, if you're not sure, you could check the discriminant. Let's check b squared minus 4ac. It's a quadratic, so the discriminant, b squared minus 4ac, tells us how many zeros it would have. If b squared minus 4ac equals 0, that means there's one way that it could be 0. If it's a positive number, it means there's two ways it could be 0. And if it was a negative number, it would mean that this couldn't be 0 at all. So let's check b squared minus 4ac. We'll do 1 squared minus 4 times 1 times 1. That's -3. That tells us that this has no real zeros. There's no real number that can make this be 0. So that factor doesn't create any restrictions. So the only restriction on the function is 1. Now let's see if we can reduce or cancel any factors. Well, I have a factor of x minus 1 here and x minus 1 here. Anything divided by itself is 1, as long as it's not 0 over 0. And this guarantees that it won't be 0 over 0, so we're allowed to reduce. So all we have left, in the numerator, I have x minus 1 times x plus 1. I suppose we could rewrite that as x squared minus 1, but I'm going to leave it in factored form. And in the denominator, I have that factor of 3, and the factor x squared plus x plus 1. So that is the original equation simplified. Make sure to write the restriction, x cannot be 1. So this is equivalent to the original expression as long as x is not 1. Okay, let's actually solve some rational equations now. So we're going to follow these 4 steps whenever we're solving rational equations. Step 1, always fully factor both sides of the equation. We may be able to simplify something to make the solving process easier, so make sure you factor first to make sure you make the question as easy as possible. Part 2, after we have everything fully factored, let's get rid of the fractions. And we can do that by multiplying both sides of the equation by a common denominator between all of the denominators in the equation. And sometimes we can use the shortcut of cross multiplying if it fits the equation we have, and I'll explain that once we get to an example where that fits. Example 3, after the fractions are gone, just continue solving it as you would any normal polynomial equation. And we should also state the restrictions throughout. So if there are any values of x that would make any of the expressions in our equation undefined, we state that as a restriction. Example 2, solve each equation. Part A is a nice easy equation to start. there's nothing that needs to be factored, we can find our restriction right away. Just look at the denominator and we'll see that x can't equal 5 over 3. 5 over 3 would make that become 0. And if the denominator is 0, that means that whole expression would be undefined. So x can't be 5 over 3. It's important to write that because it's then going to allow us to do some simplifying. I can get rid of this fraction now if I multiply both sides of this equation by that denominator. So let me write that out. So notice I multiplied the left side and the right side by 3x minus 5. When solving equations, you can do whatever you want as long as you do the same thing to both sides. So it's important we do it to both sides of the equation. And now notice on the left, I have a factor of 3x minus 5 divided by a factor of 3x minus 5. That's 1, as long as x isn't 5 over 3, which we've written, so I'm allowed to cancel those out. So all I have left on the left side is 4, so the fraction's gone. So 4 equals 4 times 3x minus 5. I suppose we could distribute that 4 in, but hey, wouldn't it be easier if we divided both sides of this equation by 4, and then those cancel? And I'm left with, on the left side, 1 equals 3x minus 5. I can then add the 5 to the other side, so I have 6 equals 3x. And then divide both sides by 3, I get x equals 2. So that's the solution to the equation. I should mention it's also important to check your solution with the restrictions and make sure we didn't find an extraneous solution. We said that x can't be 5 over 3, so if through our solving process we got 5 over 3, we would say that's an extraneous solution. It wouldn't actually be a solution to the equation. But we got x equals 2. That's not a restriction on the original equation, so that should work. I should do a left side, right side check to verify. So left side equals right side, so we found the correct solution to this equation. So this was just a check. Okay, part B. This equation doesn't need to be factored either. There's nothing to factor. I could find my restriction right away. X can't be 2. If x was 2, I'd have 6 over 0 on the left. That's undefined, so x can't be 2. Now that I've established my restriction, let's try and get rid of the fraction by multiplying both sides by the denominator. Okay, notice I'm multiplying the left side by x minus 2 and the right side by x minus 2. It's important to do both sides so that we keep the equation balanced. And it's also important that I put the whole left side in its own set of brackets and the whole right side in its own set of brackets. That way I know each of these terms, the x and the negative 1, have to be multiplied by that factor. So on the left side of the equation, x minus 2 divided by x minus 2 is 1, so I can cancel those out. So what I'm left with is 6 equals, and then on the right side of the equation, I could expand this. If we FOIL it out, I would get x squared minus x minus 2x, that's minus 3x, plus 2. It's a quadratic that we need to solve. You know how to solve quadratics, just set it to 0. So I'll subtract that 6 to the other side. 2 minus 6 is negative 4. And now this quadratic, we could solve it either using quadratic formula, or factoring is a lot quicker. The a value is 1, so I can just find numbers that multiply to c and add to b. So a product of negative 4 and a sum of negative 3 would be the numbers negative 4 and 1. So this factors to x minus 4 times x plus 1. And this product would be 0 if either of the factors were 0. So if either x minus 4 was 0, or if x plus 1 was 0. And this would be true if x was 4, and this would be true if x was negative 1. So I found two solutions for x. We should check and make sure that wasn't one of our restrictions. Our only restriction was x can't be 2. These aren't one of the restrictions, so neither of these are extraneous. These are good solutions. And we should do a left side, right side check. I won't actually take you through that, but we should be able to plug both of those numbers into this equation, and the left side should equal the right side. Part C, this is the first one where there's some factoring to do. So let's look at the left side of this equation. Let's factor the left side first. In the denominator, oh, that's the same quadratic we just had. It factors to x minus 4 times x plus 1. How about the right side of this equation? Nothing to factor from the numerator, but the denominator is a difference of squares. Now that it's fully factored, I could state my restrictions. X cannot be 4, negative 1, 1, or negative 1. So I had three restrictions there, negative 1, 1, and 4. I just like to put them in ascending order. Now that I've stated my restrictions, I could start trying to get rid of the fractions. But wait, let's hold on a second. We could actually simplify this to make this equation a little bit easier. Notice there's a factor of x plus 1 on both sides. I could technically just cancel those out, but why? Well, because if I were to multiply both sides of this equation by x plus 1, I can do that because it's the same thing to both sides. Those would reduce to 1, and those would reduce to 1. So all I would be left with on the left is x minus 5 over x minus 4 equals on the right 3x plus 2 over x minus 1. And now I have fraction equals fraction, so I'm allowed to use the shortcut of cross multiplying. If there was something like another term added or subtracted somewhere, I wouldn't be able to do cross multiplying. But since it's just fraction equals fraction, we can put the product of those two terms on one side of the equation and the product of those two terms on the other side of the equation. So that would look like x minus 5 times x minus 1 equals 3x plus 2 times x minus 4. Now this is a shortcut. We could have done this the longer way, and by the longer way I mean we could have multiplied both sides of this equation by a common denominator. A common denominator between x minus 4 and x minus 1 would be the product of those two things. So I could have multiplied both sides of this equation by x minus 4 times x minus 1. And if we did that, on this side, the x minus 4s would cancel, and on this side, the x minus 1s would cancel, and look what we're left with. X minus 1 times x minus 5, that's this. And over here, 3x plus 2 times x minus 4, that's that. So hopefully maybe now you kind of understand where cross multiplying comes from. And now we can expand both sides of this equation. I'll get a quadratic on both sides. And we have a quadratic that needs to be solved, so we have to set it to 0. So let's move all the terms to the right and collect like terms together. And now that we have a quadratic set to 0, we would try and solve it by factoring. We would look for numbers that have a product of a times c, so a product of negative 26 and a sum of negative 4. But those numbers don't exist. So that doesn't mean there's no solutions, it just means there's no rational solutions. There may be irrational solutions. We'd have to check quadratic formula to find them. So x equals negative b plus or minus the square root of b squared minus 4 times a times c, all over 2a. And then what we can do is simplify underneath the square root. Underneath the square root, I'd have 16 plus 104. So that's 120. This is all over 4. And then I should simplify the square root of 120 by checking if there's any perfect square factors of 120. And 4 divides into it 30 times. So I could split root 120 into root 4 root 30. So 2 root 30. And then I have two terms in the numerator. I could common factor out a 2 from both of those terms. And now that the numerator is factored, I could reduce 2 over 4 to make it 1 over 2. And my final answer, x equals 2 plus or minus root 30 all over 2. I could separate this into 2 plus root 30 over 2 and 2 minus root 30 over 2, but I think it would be fine just to leave our two answers combined like that. So those are the only 3 examples I had planned for solving equations, but I feel like maybe we should add one more. So I'm going to pick one out from the worksheet that looks difficult. So here's the set of practice problems that go with this lesson. Let's pick 1G, this one right here. Let's solve this one together as well. And I picked this one because we haven't done one where there were 3 fractions yet. To solve this equation, there's a bunch of ways we could do it. Let's start at least by stating our restrictions. X cannot equal 1, -1, or 0. And now that we have the restrictions, we can go ahead and try and get rid of these fractions by multiplying both sides of the equation by a common denominator. Well, what's a common denominator between 3 denominators? Well, it would be the product of all 3 of them. So I'll multiply the left side by x, 1 minus x, and x plus 1. And I'll also multiply the right side by x, 1 minus x, and x plus 1. So what I need to do now is distribute these three factors to that term and to that term. So when I multiply these three factors by this first term, do you see what cancels? The 1 minus x divided by 1 minus x. Something divided by itself is 1, so I can cancel those out. So that first product, I would have x times x plus 1 times 2, plus, when I distribute this product to this term, the x plus 1s will cancel. That will cancel with that. And so my product would just be x times 1 minus x times 3. And on the right side of the equation, that x cancels with that x. So all I'm left with on the right side is 1 minus x times x plus 1, which is actually, let me just rewrite the order of that. Let me write it as 1 plus x, just so you can see that it's a difference of squares. So now we have no fractions. Let's just expand it all and simplify. So let's look at the product of these three factors. I've got a 2 times an x, that's 2x. That 2x has to be multiplied by the x and the 1. So that would be 2x squared plus 2x. And then here, I've got a 3 times an x that has to be multiplied by the 1 and the negative x. So that would be 3x minus 3x squared. Over here, this is a difference of squares. It would just be 1 squared minus x squared. Let me look on the left side of this equation and see if anything simplifies. I've got 2x squared minus 3x squared, that's negative x squared, and 2x plus 3x, that's 5x. Now let me get like terms on the same side of the equation. Let me bring this negative x squared over. So negative x squared plus x squared plus 5x equals 1. Negative x squared plus x squared, that sum is just 0. So those are gone. All I have left is 5x equals 1. So x equals 1 over 5. So this is the answer to the equation. I could do a left side, right side check to verify. So hopefully that lesson helped. Give those practice questions a try and check your solutions after. So that's it.